temperature superconductivity. I think high temperature superconductivity is superconductivity. But what's high temperature? And now we're talking about room temperature superconductivity. So I mentioned it, and I'm going to talk a little bit from high pressure to ambient pressure, and then from very high pressure to ambient again. In other words, when people try to get this to higher and higher temperature, and people use higher and higher pressure. And now one of the ultimate goals is whether we can remove this pressure and maintain this wonderful properties of solids. That's superconductivity. So that's our aim at this moment. And so a group of my colleagues are involved in this study. I listed the name there. I think after Cameron Onnes succeeded liquefying helium, so one of the things is to use this low temperature environment to study the properties of solids. So many people put the material into this environment and see what will happen. At the time, there was three possibilities for people to speculate. One is when you cool it down, because the resistance is supposed to decrease, and then later on, it will go up. This is according to Lord Kelvin's speculation. And then Matheson said it's no, because there will be residual defects in the materials. So therefore, the resistance, instead of going back up again, and it should come saturate at low temperature. And in fact, this interpretation, at the time, people thought the electrons finally was rest because of low temperature. So therefore, stop the scattering. So the resistance goes up again. And then Duort said, no, it should continue, it drops. But this all was speculation. I specifically mentioned this, show you this picture, is that even though this is a very simple experiments, you can see here, all you have to do is just pass the current through the samples and measure the voltage. And then you look at voltage divided by I, that's Ohm's current, that's Ohm's law, will give you the resistance. And it turns out right now, talking about room temperature superconductivity, because at least at this moment, one only reported you can get to that state with a high pressure. To do very high pressure, you need lots of force. When you don't have lots of force, what you do is to reduce the sample size. And as a result, it poses serious challenges. Whether you really get zero resistance or not is not clear. So that's why I show this curve here. So then we all know it's 1999, Cameron Onnes, when he put in the mercury. And then the mercury, because at the time people thought mercury could be the purest elements, because by distillation you can get many times get very pure. So therefore they all look at pure material. It turns out the resistance decreases as originally people speculated, but then instead of going down to zero, and all of a sudden at a certain temperature, it drops to zero suddenly. And this represents a phase transition, and later on people realize it's superconducting transition. In fact, I should mention at the time, Cameron's owners didn't even believe this was a superconducting state. And he came up with lots of interpretation to explain the situation. But it turns out finally it was superconductivity in mercury with a temperature of 4.2 degrees. And this is a historical event. Well, the basic properties of superconductor, I think many of you knows this very well, but it doesn't hurt for me to repeat it. One is the resistance has to go to zero. As indicated here, when you cool it down, the resistivity goes down and all of a sudden to zero at the temperature. Tc is critical temperature. And then the other properties was the complete expulsion of externally applied magnetic field. As a result, when you put a magnet above a superconductor, and like this, it can float on top of it and without any friction. Because this zero resistivity properties, and people immediately thought of the potential application of this material for power transportation, generation, and so on. And so realized the potential technological significance of the discovery of this material. The second thing is the externally applied magnetic field can be expelled from the material, and this is what we know is Meissner effect. This actually was a very important phenomenon because otherwise, as I'll show later, because this shows that it is a real thermodynamic state. It's not just the resistance drops to zero or something, but rather it's a thermodynamic state. And as a result, London brothers and so on came up with some formula, physics formula to explain the phenomenon. And then the third one, later on, it was discovered by people in the 30s and 62, particularly Josephson Junction. And Brian Josephson basically saying that superconductivity phenomenon is a macroscopic quantum phenomenon. We know usually when you get the material, shrink it to a very small scale, it can only quantum mechanics can explain it. But superconductor, you can feel it, so basically it's a macroscopic object, but it shows the similar properties. So we call it macroscopic quantum phenomenon. Because of this, people can use it to make all kinds of devices and so on. And in order to achieve this state, one has to overcome three barriers. The first one is the transition temperature. It has to be lower than the critical temperature, T sub C. The second thing is the current passing through this material without destroying the superconducting properties. It's called critical current density. And the third one is so-called critical magnetic field. Because when the field is very strong, you can destroy the Cooper pair and therefore turn the material back to the ordinary material. So we try to get these three characteristics as high as possible. Now, I particularly show this curve is that's involved with the current debate on room temperature superconductivity. Because as I mentioned, usually the best way to demonstrate that the material is superconducting is for it to show the Meissner effect. As you can see here, for a perfect conductor, and when you cool it inside a field, and then finally when you withdraw the field, and we call it field cool, in the presence of magnetic field, when we withdraw the field, it shows some dipole effect trapped inside. So in a perfect conductor, basically the magnetic field will be resisted to enter, but once it enters, it will not go out easily, as is indicated here. But for a superconductor, it's very different. You know, for the zero field cool, in the presence of zero field, and when you cool it, it goes through a stage, and then finally at the end, there's nothing in it. But then in the presence of magnetic field, it's the same thing. It will go through, you don't see it. And so basically, the magnetic field will be expelled from within the superconductor. And this makes a big difference to tell you whether what you see is a superconductor or not. And right now, there's a strong debate on those reported room temperature superconductor, whether it's a real superconductor or it's a false. The reason is not because of the experiment itself, but rather it's the experimental conditions makes it very difficult to distinguish. But recently, there was some experiment